Homework 2, problem 6. Find the net force on the charge big Q due to all of the charges little q. We have 4 configurations to look at. For the first configuration, we see that we have a nice symmetric system of charges around here. And very specifically, we can see that for every charge above, there's one directly below. For every charge on this side, there's one on that side. It's perfectly symmetric, and the total force, because they'll all be balanced out pairwise, is obviously going to be 0. So A, I'm going to say the total force on the charge Q is going to be 0 because of pairwise cancellation. For part B, I have something very, very similar, but we take away one of the charges. Obviously, if I take away one of the charges, I still have pairwise cancellation for all other sets of charges, so that cancels with 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 that. And so the only charge left over, which will still give a force, is this charge here. And so my F, the magnitude of F, of course, is going to be little q, big Q, over 4 pi epsilon naught d squared, and its direction will be towards the missing charge. Towards the missing charge. Now, for the next problem, they make it a little bit more complicated. Instead of having 12 charges symmetrically around, they put 13 charges symmetrically around. Because they're symmetrically distributed around, we still expect the total force to be 0, but we can't use this pairwise argument to justify it. Oh, that's not D, that's C. So in order to do that now, I'm going to use an analogy from a fewer charges. I'm going to look what happens when I have 5 charges. Big charge in the middle, 5 charges around. I can add the forces. The magnitude of the force for each charge is going to be the same, so I'm going to add them just in order. I'll start with the top force. The top force is going to go directly down. This next force is going to go kind of in that direction. The next force will go in that direction, the next force in that direction, the final force back to where we started. And so if we do simple vector addition for the sum of all forces, obviously we're going to make a regular polygon out of the vectors, and it's going to come back to where we started. So the total force will be a vector of length 0. And so the total force is going to be 0. For part D, what happens when I take away one of the charges? Well, now I'm going to use a little trick. What I'm going to say is I know that the sum of all forces here is equal to 0. So the force is equal to the sum of all forces, where we're going to have I goes from 1 to 13, and we're going to have to leave out one of the forces. So that's what we're going to look at. And F sub I is the force due to any individual charge. We can rewrite this, of course, as the sum of the forces, I goes to 13, F sub I, then minus F sub j. This one would simply cancel out whatever's in here, but we've already shown in this case that all of these are going to give 0. So the total force is minus the force from the missing charge. Since we know the distance is d, again, we can make the statement that the magnitude of the force is going to be q, big Q, over 4 pi epsilon naught d squared, and it is towards the missing charge.